So tongue-in-cheek, I've named this section that we're in right now, electrical potentially confusing. Because in the past, I've had some difficulty with these concepts. We've been working on the idea that electrical potential energy and electrical potential are two different things, two different sets of units, although, just separated by a single multiplicative factor, but very different nonetheless. And so far, we've sort of exclusively been working problems associated with the electrical potential energy. And I think we've been making some headway while leaning on the experience we picked up with gravitational potential energy. The two, electrical and gravitational, are they work out very similar. But now we're going to start to deal with electrical potentials, and there's a second bit of confusion that pops up because the gravitational potential energy associated with the gravitational force is always attractive. Coulomb force is sometimes attractive, sometimes repulsive, and it has implications for how you think about the potential. And you'll see that very nicely. It's illustrated nicely in this problem. So this problem that we're taking on here has a negative charge, an electron in fact, that we first see at some point in space, and it's traveling at, I think it's 500,000 meters per second. Okay. And the trajectory is not important, but it's moving in some sort of electric field, and at a later time and at another point, it is got a speed of exactly 0. So it has been retarded and slowed to 0 by some electric field. And there's two questions. The first question is this electron moving from a region of higher potential to lower potential, or is it moving from lower potential to higher potential, which? And then second, which is what is the potential difference that accomplished this slowing down and stopping of the electron? So let's work on that first question, right? If there is an electric field, then there are regions of different potential. So initially we pick this electron up and he's got a potential of V1. Later we see him and he's got a potential of V2. Now, how the heck do you figure out if one's bigger than the other? So what you'll hold on to is the fact that the electric field always acts so that a positive charge under its influence moves in the direction of the electric field. Positive charge moves in the direction of the electric field. So let's imagine for a second that this is a positive charge, right? What's happening? Well, that positive charge is slowing down. What does that mean? That means that this that the electric field would be pointing away. If it was pointing with the positive charge, it would be accelerating, not deaccelerating, all right? But in fact, this is not a positive charge, it's an electron, a negative charge. So the field is actually in the opposite direction, and that's not as important as the fact that this is the region of higher potential. This is the region of lower potential. An electric field always points from higher to lower. Think about a parallel plate capacitor, right? Positive plate here, negative plate here. If an electron was released from that negative plate, it would rush across and picking up speed. Okay, but that's not what's happening here. The electron is essentially, if this were a parallel plate capacitor, this is the positive plate, this is the negative plate. So you really have to sort of kind of go through that set of machinations to decide whether you're in lower and higher. And of course, it all changes depending on the sign of the charge. So now let's go show that mathematically. We're going to make use of the conservation of kinetic and potential energy. This electron has some kinetic energy, it has some potential energy at both of these places. So conservation of energy says this sum is equal to 0, does not change. Let's write that like this. But let's step back and say, oh, wait a minute, this is potential energy. I really have been asked a question about the potential, but it's an easy change. If I want to represent this as a potential, then rather than U1, what I have to write in here is V1 times the charge in question. So I have to write in minus E V1. Likewise over here, KE2 plus minus E V2, right? So ultimately I'm interested in delta V. Delta V is V2 minus V1. So let me do this. Let me put this term on this side, this term on this side. I'm going to get KE1 minus KE2 is equal to the electron charge times V2 minus V1. That's the potential difference that I'm looking for. Yeah? So let me divide both sides by E. But before I do that, look, KE1 is 1/2 the mass of the electron times S1 squared. KE2 is 0, right? Delta V. And so I've got the answer to my question. Delta V is equal to minus ME S1 squared all divided by 2E. It's minus, as it should be, because V2 is less than V1. V2 minus V1 has got to be a negative number. And if you want to find out what number that is, we'll put in 9.109 times 10 to the minus 31 kilograms. We'll multiply that by 5 times 10 to the 5th quantity squared, meters squared per second squared. We'll divide by 2 times 1.6 times 10 to the minus 19th coulombs. Now just quickly, let's look at the units. This is a kilogram times a meter per second squared which is a Newton, times a meter. Newton meter is a joule. Joule per coulomb is a volt. Exactly what we want. And if you run through this problem numerically, you'll find that delta V is equal to minus 0.17 volts. All right. So for the time being, to work through these problems, asking about where the higher, where the lower potential areas are, you just have to walk through them using, using something like the technique that I just showed you. All right.